Tak, zdravím všechny. Vypadá, že to funguje. Tak, vítám z dnešní přednášky tady v podivném cyklu Goats. Omluvte prosím tady přeskakování mezi okny na začátku, nevěděl jsem, že už streamuju. Tak, stream nám začal ve 13 hodin, tak ještě jednou zdravím, moje jméno je Radomír Polách a já vám tu dneska budu povídat o zásobníkových automatech. Jak vidíte z názvu tohoto videa, jedná se o determinizaci, Visibly Pushdown zásobníkových automatů a real-time Height-deterministic zásobníkových automatů. A nejdůležitější věc je to for Goats, takže pro členy tady tohoto sezení. Tak, předpokládám, že všichni jsou nějakým způsobem seznámeni s tím, co jsou to zásobníkové automaty, a než začnu, tak bych krátce to nějak stručně popsal. Určitě všichni znáte konečné automaty mají nějaké přechody a stavy a z počátečního stavu postupně přechází přes jednotlivé přechody do různých stavů. Pokud skončí ve stavu, který je koncový, tak řetězec přijímají, pokud ne, tak řetězec nepřijímají. U těch zásobníkových automatů tam je to podobné, jenom s tím, že ty zásobníkové automaty navíc mají zásobník. Tím se všechno komplikuje, oni si při těch přechodech můžou nějakou informaci ukládat na vrchol toho zásobníku postupně a zase si v některých stavech odstraňovat. Tak, já mám tady takový zvláštní setup, teď, že koukám na svoje video na tom YouTube, které je zpožděné, takže mě to trochu mate, takže se omlouvám za případné nedostatky svého projevu. Tak, zatím vypadá, že všechno funguje. Tak, tím pádem je to úvod za námi. Já teď postupně povím něco o těch jednotlivých skupinách automatů a jak se mezi sebou liší, protože existují 3 skupiny těch zásobníkových automatů, které se dají determinizovat. První z nich jsou input driven zásobníkové automaty, pak máme visibly pushdown zásobníkové automaty a pak máme height-deterministic zásobníkové automaty. Já teď všechny ty skupiny projdu a pak se budu bavit o té jejich determinizaci a pak vám povím i o našem výzkumu, který se týká tady té determinizace zásobníkových automatů a ukážu vám nějaké informace o tom, jaké dřívější papery si můžete přečíst a Okay, so somebody does not speak Czech, so we can switch to English now, okay? So, again, this talk will be about pushdown automata. Most importantly, it will be about the determinization of visibly pushdown automata and height-deterministic pushdown automata for Goats. So for the people who are attending this session. So, you are probably familiar with pushdown automata. They are similar to the finite automata, but they have a pushdown store into which you can push and pop symbols, and that can influence how the automaton works. This talk will be mostly about these determinisable classes of pushdown automata. So far there are 3 different classes of the pushdown automata, which we know are determinisable, and we know the algorithm how to determinize them. These are input-driven pushdown automata, visibly pushdown automata, and height-deterministic pushdown automata. First, I will talk about these different classes of pushdown automata and how are they different between these different classes. So, the determinization of the pushdown automata. The most simple class of the pushdown automata are these input-driven pushdown automata. This is not an important. Input-driven pushdown automata are basically like the finite automata, but there is a pushdown store operation added to the transitions, but the pushdown store operation is determined solely by the input symbol. So this is like basically I have classic finite automaton, all the decisions are done by the input symbol, but there's an additional operation done on each transition. The operation does not influence the decision on which we chose what transition to make, so it is solely determined by the input symbol. The determinization is done in a very same way as is done for the finite automata. These are basically just a simple extension of the finite automata. Then there is much important group, and this is the visibly pushdown automata. These are real pushdown automata in a way that the pushdown operation is partially responsible for deciding which operation we can take, which transition we can take in the automaton. In a way that, for example, if some specific symbols is on the pushdown store top, we decide the transition based on that symbol. This automata works in a way that we have a partitioned input alphabet. We have 3 separate partitions of the alphabet, and each of these partitions is responsible for a specific pushdown store operation. So these are 3 parts of the alphabet, and each part is associated with a different pushdown store operation. AC is a finite set of call, or we can call push symbols. AR is a finite set of return pop symbols, and AL is a finite set of what we call local, sometimes internal symbols. Basically, it's associated in a way that AC is always bundled with some push operation, AR is always bundled with some pop operation, and AL is always bundled with some operation which does not change the depth of the pushdown store. We can summarize it by saying that the type of the pushdown store operations is determined by the input symbol and not the operation itself. The next class of the pushdown automata are the Height-deterministic pushdown automata. This is basically a generalization of the visibly pushdown automata. Input alphabet is not partitioned here. Instead, we impose a different condition. We impose a condition that for every input word, the depth of the pushdown store is the same for all non-deterministic paths. This was true for the visibly pushdown automata as well, because the symbol influenced the type of the operation. So if we had a symbol from AC, we would always do push of one symbol, so the depth of the pushdown store will always stay the same for the same word, regardless of the non-deterministic path taken. Now we are completely disregarding the partitioning of the alphabet into the 3 parts, but instead we impose just this condition that for every input word, the depth of the pushdown store is the same for all non-deterministic paths. So regardless of what non-deterministic path you take in the pushdown automaton, the depth of the pushdown store will always be the same. We can generalize it by saying that the type of the pushdown store operation is determined by input symbol for that group of corresponding states. And this is the important thing. It is a group of corresponding states, and this group of corresponding states actually corresponds to what we call D subsets in the finite automata. And the D subsets in the finite automata are sets of states which corresponds to the states of the determinized automaton. If you remember how the finite automata are determinized, finite automata are determinized in a way that each state of the deterministic finite automaton is consists from several states of the original non-deterministic automaton. It is like a simulation that we are accepting a string using the non-deterministic automaton. We can be at several states at once. So if we want to determinate automaton, we have to introduce states which consists of several states of the original non-deterministic automaton. Same thing holds for these pushdown automata, and this generalized group of Height-deterministic pushdown automata works in a way that the type of the pushdown store operation is determined by input symbol for a group of corresponding states, and this group of corresponding states is a group of states which basically corresponds to the states in which you can be for an input in the non-deterministic automaton. So each state in which you can be in the non-deterministic automaton are this group of the corresponding state for which the pushdown store operation is determined. So here we've disregarded the partitioning of the alphabet into 3 parts, but instead we impose this condition. So this was the talk about the different groups of the pushdown automata we know, and we know how to determine them, and then there will be a talk about the determinization. I have here a comparison between the determinization of the finite automata and the determinization of the pushdown store automata. On the left, I have a simple example of the non-deterministic part of the pushdown, non-deterministic part of the finite automaton and deterministic part of the finite automaton. These are just the snippets of the automata, so you can see that the state 3 on the left is connected to states 4, 5, and 6, and it is non-deterministic because there is a same symbol for all of these transitions. So if we were to determinize it as a finite automaton, we would get these two states, 3 and 4, 5, 6. This is what I was talking about before. This is the subset. This is the state which corresponds to the several state of the non-deterministic automaton. This is the subset, and it becomes a single state in our deterministic finite automaton. The pushdown automata are a little more complicated because there is that pushdown operation. And if you look at this example on the right, you can see that the state 3 in the middle can be passed different ways. First way is we can pass from 2 to 3 to 5, because in 2 to 3 B is pushed, and in 3 to 5 B is popped from the pushdown store. Or we can pass from 1 to 3 and 3 to 4, because in 1 to 2 A is pushed into the pushdown store, and then in 3 to 5 A is popped from the pushdown store. So we can pass either the 2, 3, 5 or 1, 3, 4. And this has to be taken into account when making a deterministic automaton. So if it was just a finite automaton, these states 1 and 2 would be matched together, and 4 and 5 would be matched together, similarly as it was on the left side in the finite automaton. But because this is a pushdown store operation, the important thing here is also the pushdown operation, which influences what paths can be actually taken in the pushdown automaton. And if you look below at the deterministic version of this pushdown automaton, you will see that the states 1 and 2 will be merged together, but states 4 and 5 will not be merged together. And the important difference you will see here is the states in the deterministic pushdown store automaton are not sets of states of the original automaton, but instead are sets of pairs of the states of the non-deterministic pushdown automaton. See, here we have 0, 0, here we have 1, 1, here we have 2, 2, 3, 3, 0, 6, 2, 4, 2, 5, 1, 4, 1, 5. And what it means is that the second field of each pair is the same thing as was this subset in the finite automata. But there is an additional information which connects appropriate push and pop transitions. So there was a push transitions from 2 to 3 and pop transitions for 3 to 5. And this path from 2 to 3 to 3 to 5 connects the automaton in a way that between the states 2 and 5 there will be the same depth of the pushdown store, and this is reflected in our states of the deterministic pushdown automaton. It gives us info 2, 4, 2, 5. It gives us info that these states are on the same depth. It basically connects us these states which shares the same depth of the pushdown store. So this will be hidden 1, 4, 1, 5, 2, 4, 2, 5. Similarly, between the states 0 and 6, it holds the same property, because we will go up pushdown store, down pushdown store, up pushdown store, down pushdown store. So the depth of the pushdown store between the 0 and 6 is the same. So in the set for the new state 6, there will be 0, 6. It would mean that it is a state which was created from state 6, and it is locally accessible, meaning that the pushdown store depth doesn't change from the state 0. So there is an additional information in our D subsets, and it is the information about the paths in the non-deterministic pushdown automaton, and it gives us the information about states on the same depth of the pushdown store. It basically gives us information about corresponding push and pop transitions, which leads from and to the same depth of the pushdown store. So this is basically the basic idea about how the determinization of the pushdown store automata work. Here we have some quick information about the subsets R component, S component. So in the pushdown automata, we usually doesn't use the term D subsets. We use the R component and S component. The R component is basically what we called D subsets in the finite automata, is the second field of each pair. So it is the set of the second fields from each pair. And the S component, which is more important, is the set of pairs. So this basically replaces the D subsets in the pushdown automata. So here we have a quick summary of the determinization properties. You probably remember what is the complexity on the number of states for the finite automata is O 2 to the power of n states. So we basically have the D subsets, and D subsets can contain each state of the non-deterministic pushdown automaton. So basically each state is or is not there, so it is 2 to the power of n. So there is an exponential expansion on the number of states. It is similar for the pushdown automata, but the exponential expansion is much larger. It is in general, as it was defined, 2 to the power of n to the power of 2 plus n on the number of states, and appropriately on the number of pushdown store symbols and transitions. It can be brought down to the 2 to the power of n to the power of 2 by some improvements, like disregarding the R component, because the information is completely stored in the S component as well. So 2 to the power of n to the power of 2. So it is pretty big exponential expansion, but in reality it is not usually that bad. Similar with finite automata, usually don't see the exponential expansion. There is like 2-3 times the number of states, but in worst case it can be actually as bad. It can be 2 to the power of n even for the finite automata. How is the determinization done? This is the quickly going through the math behind the determinization. We basically create a deterministic automaton in a way that we define how each set Q A G delta Q0 bottom of the pushdown store and set of the final states look like. I am not going in the detail on this. You can all study the articles related to this. They will be here in a moment. But the idea here is that we have exact math how to calculate local transitions, push transition, pop transition for all states of the non-deterministic automaton to create the deterministic automaton. It is not very efficient, it is just a math. It works with Cartesian products, so it will create all of the possible states and transitions which can be there. The automaton will be deterministic, but it is not usually a way how you want to approach the determinization. So my work and work of my colleagues is basically how to make the determinization of the pushdown store automata more like the determinization of finite automata. If you remember how you determinize finite automata, you basically create the initial state of the deterministic automaton and then you basically expand only the accessible states of the deterministic automaton and not all of the possible states which can be there. And we did the same thing for the pushdown automata. Here is an example of our solution. Here at the bottom you have the articles you can study for the definition of visibly pushdown languages, some improvements, a tighter bound for the determinization of visibly pushdown automata, and look into the visibly pushdown automata library. This was some attempt by some Chinese college students to implement this exactly as it was written in the prose, but it has very bad exponential expansion, which is guaranteed to basically not allow you to have more than 2 states in your automaton. Our approach is the approach based on the idea in the finite automata. So firstly we omit the impossible states, which means empty S or R component, then impossible pushdown store symbols, empty S or R component. We create pop transitions only for existing pushdown store symbols, so we track pushdown store symbols that actually appear in the deterministic pushdown automaton and do pop transitions only for them. And the most important thing here is not create pop transitions for all of the pushdown store symbols created, but only create them for the pushdown store symbols that can actually appear at the top of the pushdown store for each state. So this is the most important thing. Pop transitions are created only for possible pushdown store symbols, meaning for those pushdown store symbols that can actually appear at the top of the pushdown store for each state. We only access the states which are accessible, and we construct the automata incrementally in a way done in finite automata. We are using the improvements from the Nguyen Van Tang, which means removing the R component and bringing the upper bound to the O2 to the power of n to the power of 2 number of states. So this is our solution. How we do it? We do it in a nice way. We track the pushdown store symbols. It is like a set of symbols that can appear at the top of the pushdown store for each state, and we track it during the whole construction of the pushdown store automaton for each state, and in each operation when we do pop transitions, we only do pop transitions for those pushdown store symbols that can actually appear there. The outline of the algorithm is presented here, but I have some pseudocode which is, I think, more descriptive on the one of the next slides, so I will get to it. But firstly, I will talk about how we track the possible pushdown store top symbols. Look at this simple example I have here. I have here a snippet of the automaton, and I have some, it is visually descriptive as all of the arrows leading to the top are push transitions, and all of the arrows leading to the bottom are the pop transitions. So this basically means we have the same level, same depth of the pushdown store on this level, and we can push, do some work which does not change the depth between the states 2 and 3. So it means that this depth between the states 2 and 3 will be always above or the same, and it will be the same between the states 2 and 3. And then we do pop, and then we do some local operation, then we do push, something, pop, and something. And if you look at this, you will see some pattern here. Like if the 2 and 3 has the same pushdown store depth, then 1 and 4 will have same pushdown store depth as well. And same goes for 6 and 7 and 5 and 8. And if these states 2 and 3 has the same depth of the pushdown store, and pushdown store was never below this depth, then the symbols that could appear at the top of the pushdown store in state 2 are exactly the same that can appear at the top of the pushdown store for state 3. And same goes for 1 and 4. So there are basically groups of states that gets connected together, and they share their pushdown store symbols, meaning the symbols that can appear at the top of the pushdown store. We call this local connection, and this local connection can be closed under the closure operation, and in that way we can represent it even more efficiently. For example, in implementation we can do some linking between these sets to store the information about efficient way. And if we have this information available, we can then do the determinization very easily. Here is a non-deterministic automaton, which is a pushdown store automaton. And we start by creating in the initial state of the deterministic pushdown store automaton, this state is created as an identity of initial states of the non-deterministic automaton. So only one state was initial state in our non-deterministic automaton. It was state 0, so our initial state will be 0, 0 as an identity. And we will track the top of the pushdown store set T, and we will input first just the bottom of the stack symbol. So this is our bottom of the stack symbol. And in next step we do local and push transitions by the rules from the proofs, and we recalculate our tops of the pushdown store sets. And when we do other states, creating other, we will recalculate again the tops of the pushdown store. And then when it comes to make the pop transitions, we do pop transitions only for the pushdown store symbols which we know can appear at the top of the pushdown store for each of the states. So this significantly limits the number of transitions created and states explored. We are actually accessing only states and transitions which are accessible. Nothing more will be created than what is actually accessible, and this will reduce the resulting automaton significantly. The final states are then set as the states which contains in the second field a state which was final in the non-deterministic version of the automaton. So all states which contains 1 in the second field will be final, so it is state 0, 1 and 0, 0, 0, 1. And we are done with this example basically. And here is the promised outline of the algorithm. We use Q dirty and set clean. Dirty basically contains all states which does not have even the vocal and call transitions processed, and the clean contains states which have already the pop transitions created, and we basically loop over the dirty until it empties, and we always do the vocal and call transitions, and if the state was affected we do also the pop transitions, but only for the pushdown store stop symbols that are the part of the pushdown store top symbol set for each state. Finally, we set appropriately final states. How it behaves in reality. Our solution is very nice because it creates only those accessible states. So for example, numbers of transitions in the original paper from Alur and Madhusudan created by the Cartesian product for this little sample gives you 64. Improvements from Van Nguyen Wantang give you 16. Implementation from Gan Nguyen gives you 45. But as we only examine the states which are actually accessible, we get 3 states, and we get 8 transitions for this example, as you have seen. So it is still exponential in reality, but normal practical examples give you, I would say, usable results. You can actually use this method of ours to process non-deterministic automata, create a deterministic automaton, and run this automaton to accept some strings. We did some larger testing on 3 different problems, or on the problems of regulatory expression and on the problems with 3 patterns. Here we have non-deterministic automata, and here we have deterministic automata created by our algorithm. As you can see, the exponential expansion can be easily seen from, for example, in the most complicated example I have here, from 9 states and 26 transitions we went to 458 states and 10,005 transitions. So it is still exponential and it's pretty big. But if you want to make an in linear time accepting, it is an available way for you to do it, because then you can use this deterministic automaton even if it is big to do the linear time accepting using the deterministic automaton. We have some observations on some upper bounds, as only the pairs of q primes q that are in the lambda closure, that q prime is the lambda closure of q, can appear as an element of S component. We can actually examine our non-deterministic automaton and bring the upper bound from that exponential to little lower. There can be actually 2 to the size of the L, maximum number of states, where L is the set of distinct pairs of the locally closed states. So this is like an case-specific upper bound for when you want to know how bad your deterministic automaton can be, because usually it's much better than the actual upper bound. Here are some calculations of our improved upper bound. For example, for those problems from the previous slides, improved upper bound brings the number of states a little lower, but as you see, it's actually still exponential. It's due to the size of the L, so it is still exponential. So, but it is several orders of magnitude better than the general upper bound for our cases. So here comes the conclusion. Our automata produced by the determinization are quite small, are built incrementally. The modified version is applicable for both the VPDAs and RHPDAs, meaning the visibly pushdown automata and real-time height-deterministic pushdown automata. Similar approach may be possible for other normalizations of visibly pushdown and real-time height-deterministic pushdown automata, and similar approach may be also possible for different classes of pushdown automata. We have also some ideas about the pushdown automata minimization done using the information gathered from the pushdown store top symbols. I'm making some paper about that. And here are our publications you can review. We have 2 articles, a new algorithm for the determinization of visibly pushdown automata and an efficient determinization of visibly and height-deterministic pushdown automata. Or you can also go back to the papers I mentioned before. There are proofs from Alur and Madhusudan for the visibly pushdown automata, and there is one paper I have not mentioned here, and it is for Nowotka and Srba about real-time height-deterministic pushdown automata. I have to improve these slides before I submit them. I will add that one additional article here as well, because the height-deterministic and visibly pushdown automata are similar in the way that height-deterministic pushdown automata are just the generalization. Basically same principles with slight modification holds also for them. So originally this method was only for the visibly pushdown automata, but we have extended it to cover the height-deterministic pushdown automata as well. So this was this, and I think that's probably it. So I may have fit into the 40 minutes nicely. I have 2 more minutes, so thank you for your attention. I think it was quite quick to cover all what I wanted to tell you. You can look more about the topics of the processing trees on our website arbology.org, and you can go through the articles mentioned here, either for our own articles or the articles from some previous works. And thank you for your attention, and we may see each other. Yes, do you have any questions before we end? Anybody has something? Forgive me if I was speaking too fast. I wanted to fit into the 40-minute window, so yeah, implementation is part of the ARIP. There was some initial implementations in the written in Java for some testing, but when ARIP was available, my colleagues rewrote them for the ARIP. So actually you can try the determinization from both the visibly and height-deterministic pushdown automata in the ARIP. There are also some problems for the tree patterns and for the regular tree expression that actually are translated into the non-deterministic height deterministic pushdown automata, so that you have like a full chain. You have some problem, you can transform it into the non-deterministic pushdown automata and determinize it, and you can try it in the ALIP. So it is not like it's on paper only, it is also a part of the implementation in the automata library ALIP developed on the faculty by my colleagues, mostly by Mr. Travníček and Mr. Pecka, so you can try implementation. So thank you very much for your attention and for this time, and we may see each other some other time. Thank you.